In our chapter on work and energy, we have one more form of energy that we need to throw into the mix. In this last section, you've seen how work can cross the boundary and add energy to a system, or work can cross the boundary and take energy out of the system, and that as the system runs, there will be changes of energy within the system. We've done that with kinetic, gravitational potential, and elastic potential. Now, the last form of mechanical energy that we want to talk about is thermal energy, but it's going to be specifically thermal energy as it relates to friction. We've already talked about the definition of thermal energy, but let me just say it again. It is the sum of the random kinetic energy of the molecules and atoms in a system. The sum of the, and we'll say random because it is random. Kinetic energy, the motion is very random. Kinetic energy of the particles. When I say particles, I mean formula units, atoms, molecules, ions, whatever, particles in a system. One way of increasing thermal energy in a system, and that's the way we'll be talking about this time, I can increase it by radiation, I can increase it by convection, by conduction, but one way of increasing it is also through friction. We'll be talking about the other ways that we manage heat or thermal energy, two different terms actually, when we get into the next chapter. Right now we're just worrying about friction in a system. Now I want to talk to you about, I'm going to make this derivation pretty simple. So I want to talk to you about the setup for this derivation first. You're given is a block pulled horizontally at constant speed. Of course, the constant speed tells me that there is no delta KE. Horizontally means that there is no delta PEG. And yeah, I don't have a spring, so there's no elastic potential. Now let's go ahead and jump into our givens. We're going to go back to the W is equal to F delta R cosine theta. It's because I want you to remember originally where does all this come from, and it is the definition of work. Now we also know that this time delta R is actually going to be delta X, and it's delta X because we're pulling it horizontally, so that's given. And W is equal to F sub K delta X. The only force to overcome is friction. I have no other forces acting on this since I'm pulling horizontally. I don't have to worry about weight. I don't have to worry about the normal force or the force of contact. And so my only two forces acting in my system, according to my given, is the force of the push or pull on the block, and that has to be in balance with the force of friction. Otherwise, if it were imbalanced, it would be accelerating. So the only force to overcome is friction, and they have to be equal to each other because there is no acceleration, constant speed. All right, so the next thing that I have, and I'm actually going to eliminate a lot of these right now. I'm going to tighten this up a little bit. All of my work is going into overcoming thermal energy. That's my given. I have no other form of energy that is at play in this. All my other forms of energy have been taken off the table. So if that's the case, then thermal energy is going to be equal to F sub K delta X. And this is substitution. Now there's a lot more lines because I've done this a different way in the past, And I've decided, just for the interest of brevity this year, we're going to tighten this up a little bit. So really, this one's pretty straightforward. I have one force that I have to overcome. That force is the force of friction. And they're in balance because they're constant speed, and it's moving horizontally, so it's delta x. Excuse me. So this is my derivation, and this is going to be my working formula then. E thermal is F sub k delta x. And the change in thermal energy due to friction when an object moves a distance delta x across another surface is, again, I'm just going to write this out for you, E thermal, which is equal to the force of friction times the length that it's being moved. And the thermal energy is shared by both surfaces. If this is friction, then you understand, if this is caused by friction, then you understand when you rub your hands together, both hands get warm, not just one. So the thermal energy is shared by both surfaces. And delta x is the distance the object moves. Doesn't matter what direction it's moving in. It can be moving up a slant, it can be moving horizontally, but delta x is the distance the object moves. For the interest of our derivation, we made it horizontal, but it does not have to be horizontal in our problems. All right, so let's go ahead and look at 8.9 to see how we're going to throw this together. And you're going to find with the ones that I'm doing in the notes, you're going to find that it is going to be a work energy problem. I'm going to jump right into E thermal as a part of W is equal to delta KE plus delta PEG, delta PES plus delta E thermal. All right, let's see what this looks like. This one is actually 8.10. 8.10. We never did 8.9. I'll have to go back and look at that. 8.10, an 1,100 kilogram car traveling at 18 meters per second skids to a stop on a level road at a distance of 24 meters. Calculate the average kinetic friction force, not thermal energy. It's specifically asking for the friction force acting on the car as it stops. I'm going to do my normal work energy process. First thing I'm going to do is a drawing, and I put into the drawing all of the factors that I need, although I did forget to put in there that it's 1,100 kilograms, so let me mark that in there as well. And I have to ask myself, is there something outside the car working on the car? Friction is built into the system. Let me say that again. Friction is going to be built into the system, and that's not going to be something acting outside of it. All of the heat that's generated through this process is from the system itself, the heat of the brakes, the heat of the tires on the road, the friction created by those moving parts, and that's a part of the system. So in this case, work is equal to 0. If the only thing acting on the system to stop it or to slow it down is the brakes or whatever, you have no work acting on the object. All right, so I've got work is equal to 0. Now I have to go through all of my other forms of energy and see what we have to say about that. So W is equal to delta KE plus delta PEG plus delta PES plus delta E thermal. Work we've already said is 0. Delta KE, it's starting at 18 meters per second and ending at 0. So I am taking the kinetic energy out of the system. That's going to be negative in my prediction. It's on a flat surface, so there's no delta PEG. And there's no spring involved, so it's only E thermal. Now you already know just by looking at this that it's going to have to be positive. E thermal just means the transfer of, I want to be careful how I say this for the next chapter. Thermal energy is the sum total of the kinetic energy of the particles. If there is a transfer going on, then we're talking about heat. and I am transferring heat into the system. So I'm going to use the word heat here, even though it's thermal energy that we're talking about, and you will get the distinction between the two of those in the next chapter. But when you rub your hands together and you're creating friction with your hands rubbing together, do your hands ever get colder? Do I ever take thermal energy out of the system by friction? Can friction make an object colder? No. It always is going to be positive. If there is friction in the system, my thermal energy is always, always, always positive. Thermal energy is always positive. So you can go back to that page, the page before, or several pages before. In fact, let me find it for you here. Where it is just a page before, where we have the E thermal. When is that positive? Now you can say always. It is always positive. There will never be a time when thermal energy is going to be negative. Yeah, that was the page before. All right, so I know that my thermal energy is positive. Always positive. Always positive. So now let's work through what these are and what they mean. Let's do the delta KE problem first. Delta KE is equal to 1/2 m v squared minus v naught squared, which is 1/2 times 1100, and my v squared is 0, so it's going to be, I'm going to put my negative out front just so I don't forget it, but that negative is not squared, so it can come out front. And v naught is 18, so it's times 18 quantity squared. When you do the math, you end up with a negative 1.78 times 10 to the 5th joules. Now my delta E thermal is my force of kinetic friction. This is a force going to be measured in newtons. My force of kinetic friction times the distance that a friction is being applied over. This is what I'm looking for. I don't know this. So I have 24 delta x, which my delta x is, I'm sorry, let me put that backwards to start with just so we're not confused. My f sub k is what I don't know, and my delta x is 24. I like writing that in the front because you always put coefficients up front. But for right now, so that you're getting the distinction, it's f sub k times 24. Now I'm going to go ahead and put this into my work energy equation. So what I have then is 0 is equal to a negative 1.78 times 10 to the 5th, 0, negative 1.8 times 10 to the 5th, plus, excuse me, 24 f sub k. I'll move that over. 1.78 times 10 to the 5th is equal to 24 f sub k. F sub k is equal to 7,420 newtons. This is a force. Force is measured in newtons. Now, this is going to be called friction force. It can be called resistive force, because it is going to be a force that is going to be resisting motion or hindering motion. I don't know why that's out of focus. It's going to be the force that's going to be resisting motion. It's going to, in my car, it's what stopped the car. It was the only thing that stopped the car, the force of friction. And if it's talking about thermal energy, that's going to be measured in joules, and it is the friction force times the length or the distance that it's traveling. But this will be called the friction force. And let's try another one on the next page. Now I have a skier going up a slope, and again we're going to build a little bit of resistance into this with friction. So it says, you wish to build a ski lift for a small hill next to your living quarters. The cable to pull a 100 kilogram skier, and I don't have his mass on here, let me put that in, a 100 kilogram skier is up a hill inclined at an angle of 20 degrees to the horizontal. The skier speed is 0 at the bottom and 6 meters per second at the top. The hill is 50 meters long, and a 150 Newton friction force opposes the skier's motion. Calculate the average tension on the cable as pulling the skier. So the first question that you're going to ask is there work? Well, I can already see that there's something outside the system pulling him up. There's a force acting on him that's pulling him up. And that's what we're looking for, is the tension or the force on that rope. So I end up saying that work is not equal to 0. And I'm going to have to calculate what it is, which I'll do that in a minute. So work is not equal to 0 is equal to delta KE plus delta PEG plus delta PES plus delta E thermal. And I ask myself in each of these cases, is this existent or apparent in this problem? By the way, I'm also wanting to identify, is work positive or negative? Work is the force is going in this direction and the motion is in this direction. So my work is going to be positive because it's cosine 0. So it's going to be a positive work. Delta KE, I have 0 meters per second here, 6 meters per second here. So that's going to be positive. I am increasing my speed. I'm also increasing my height. So this is positive. There's no conversation about a spring in here. And is there conversation about friction? Yes, it actually gives you a friction force. So as soon as you know that there's a friction force, then you have to calculate what thermal energy is. Thermal energy is always positive. Again, if you had wondered, is there or is there not work, the only way all of these can be positive on this side is if there's something creating those numbers on this side. So let's work through what the different forms are going to be. We'll start with work. Work is equal to F delta R cosine theta. And in this case, then it's going to be F, which I don't know, times 50 cosine of 0, which is 50F. And it's positive because it's working with motion. Delta KE is equal to 1/2 m v squared minus v naught squared, which is equal to 1/2 times 11, no, that was my last one, times 100 times my v naught is 0, so I can cancel that out, times 6 squared. And that's going to end up being, I have the wrong one in front of me. Let me help myself out here. So it's going to end up being 1,800 joules. Delta PEG is going to equal mg, and my h I'm going to have to calculate. So the mass is 100 times 9.81 times my slant, which is 50, sine of 20. Remember that when you're not given the height, then you utilize your trig functions, and my angle is opposite the side I'm looking for, so that's why it's sine, and I know my hypotenuse. That's how I got 50 sine of 20. If you need some more help with those, let me know. This ends up being 1.68 times 10 to the 4th joules. And then finally, delta E thermal is F sub K delta X. F sub K is 150, they gave that to you, times 50, which ends up equaling, excuse me, 7,500 joules. So I'm going to go ahead and put this now into my work energy equation. In place of W, I'm going to put 50F is equal to 1,800 plus 1.68 times 10 to the 4th plus 7,500. And when you do all the math, you end up with F is equal to 522 newtons, which isn't really all that much. It actually is, it's actually not going to take a lot of work on their part to pull them up. 522 newtons isn't a lot. All right, now, with these problems, I just want to tip you off with this. Again, this is the force of friction. And when you're seeing a resistive force or a friction force, you know it belongs here. You can have other forces now in the problem, and you have to identify, excuse me, is the force being talked about friction force, or is it a force that is a part of work that is either crossing the boundary to add energy or crossing the boundary to take energy away? Your homework for this is going to be, it's going to be 63, 65. Nope, I have that wrong. I'm so sorry. That's the power problems, and I don't think you're quite ready for those. These are going to be 49 through 56. Still a lot, but not as many as before. 49 through 56. Note that number 52 is asking for a resistive force. So, of course, it's asking for F sub k here. And I would encourage you to set number 55 up as a two-event problem. Set number 55 up as a two-event problem. Let me know if you need anything with these, and certainly during our Zoom time today, you're going to want to jump on and have me check your homework, ones that you're not sure of, before you officially turn it in. I'm going to let you do that for tomorrow's Zoom, and then you can wait until Thursday to turn that in if you would like. I'm anticipating the test to be next Tuesday. I would ask you to come in just sometime, either Monday, Tuesday, or Wednesday to take the test, but plan on taking it on one of those days after school. If you can't come into school for it, then let me know, but I would really appreciate it if you could do it that way. Okay, let me know what you have decided with that and what you need. All right, bye-bye.